Moving on to section 4.2, polynomial functions and graphs. Now we're going to put some things together and that'll help us analyze polynomial functions and graphs. And we're also going to look at piecewise functions again. Remember, a polynomial function is a function in this form where n is going to be a positive or a non-negative integer, and these numbers in front of the powers of x have to be a real number. They can't be an imaginary number. A turning point, we said, is this maximum or minimum value. That's where your graph changes directions from increasing to decreasing or decreasing to increasing. Your book refers to these as hills or valleys. I prefer calling them maximums and minimums because that's what they are. Is this point at negative 2, 8 a local or an absolute maximum? It's local. And then this point right here, that's a local minimum. If we know something about the degree of the polynomial, remember the degree is the highest power of x, we can tell something about the end behavior and the turning points. For this graph, we would say the end behavior here, it's what's happening as x goes off to negative infinity. As x goes off to negative infinity, what is the y doing? It's going to negative infinity as well. The way that I would represent that is as x approaches negative infinity, y approaches negative infinity. So I would write as x approaches negative infinity, f of x approaches negative infinity. Over here, as x goes off to positive infinity, the y is going off to positive infinity. So we would say for the end behavior of this graph, as x approaches infinity, f of x approaches infinity as well. They're going in the same direction. If your polynomial has an odd degree, odd meaning 1, 3, 5, 7, 9, what that means is that your ends are going to point in opposite directions. The end behavior will be such that the ends point in opposite directions. Let the alliteration help you out here. Odd degree, opposite directions. You see how this one's pointing down and this one's pointing up? This one's pointing up, this one's pointing down. Our endpoints are going to go in opposite directions. Furthermore, you can tell something about the leading coefficient. Remember, the leading coefficient is the number that the highest power of x is multiplied by. I'm going to let A represent the leading coefficient. For this one, notice how we start at the bottom and work our way up. The leading coefficient here would be positive, because if you start at the bottom and work your way up, you're a positive person. This one, our leading coefficient would be negative. Even a negative person, if they start out at the top, they'll still find a way to work their way to the bottom, won't they? Think about positive and negative peoples. Use that personification to help you remember something about the directions. So remember, positive people start at the bottom and work their way up. Negative people start at the top and work their way down. And so you can tell that this would be an odd degree polynomial, and it has a negative leading coefficient. Both of these would be odd degree polynomials because the endpoints are going in opposite directions, but we'd have a positive leading coefficient here because of the direction that we're going. If a function has an even degree, the endpoints are moving in the same direction. So you see on this graph, both of the endpoints are pointing up. On this one, both are pointing down, and on this one, both are pointing down. Whether or not these endpoints point up or down tell you something about the sign of the leading coefficient. This would be an even polynomial where A, the leading coefficient, would be positive. This would be a leading coefficient where A is negative. Here's the corny way you remember it. Positive people smile, negative people frown. We're only looking at the endpoints. We could have as many twists and turns in between as you want. But if the endpoints are going in the same direction, we have an even degree polynomial. Square, 4th power, 6th power, 8th power. That's from looking at the graph. Another thing we can determine is by looking at the x-intercepts, the highest power of the polynomial will be equal to, it'll be greater than or equal to the number of x-intercepts. So the graph of a polynomial function of degree n with n greater than or equal to 1 has at most n x-intercepts. So the number of x-intercepts will give you a clue as to what the minimum degree of the polynomial will be. And it has at most n minus 1 turning points. Let's go back and look at these graphs. Here we have 1, 2, 3, 4 x-intercepts. So the smallest degree that this polynomial could be is x to the 4th. And there's 1, 2, 3 turning points. So we have to have one fewer turning points than the degree. So this would be a 4th degree. Up here we had 1, 2, 3, 4 turning points, so this has to be at least a fifth degree polynomial. There's 1, 2, 3, 4, 5 x-intercepts, so there's got to be at least a fifth degree. In example 1, we're asked to use the graph of the polynomial function to answer the following questions. Part A says for us to determine the number of turning points and then estimate the x-intercepts. So how many turning points do we have here? There's 1, there's 1, and there's 1. So there's a total of 3 turning points. And I have x-intercepts where this point is at -4, and then I have another one at -2, another one at 2, and another one at 3. So with 4 x-intercepts and 3 turning points, can you tell me what the degree of this polynomial might be? What the lowest degree would be? 4, x to the 4. The leading coefficient, is that going to be positive or negative? It's going to be positive because both of my endpoints are pointing up and it looks like a smile. So here we would say that A is positive and the minimum degree would be 4. In example 2, we're asked to use the graph of the polynomial function and do the same thing. Part A says how many turning points and x-intercepts are there? Well, let's count the turning points first. So there's 1, 2, 3, 4 turning points, and how many x-intercepts? There's 1, 2, 3, 4 x-intercepts. Is the leading coefficient to this polynomial going to be positive or negative? What about the degree? Is the degree going to be even or odd? The degree is odd because my endpoints are moving in opposite directions, and the leading coefficient, I start at the top and work my way down. Does that sound positive or negative? So the leading coefficient would be negative. To me, it's easier to answer the degree question first and then look for the sign of the leading coefficient. It's odd because they're going in opposite directions, and if you start at the top and work your way down, that's negative. Part C asks us to determine the minimum degree of f. So I have a total of 1, 2, 3, 4 x-intercepts, but when the graph just touches, that's called a double root. If it just touches the x-axis and doesn't go across. So there's actually 5. This would be a degree of 5. Because remember, you have to have 1 fewer turning point than your degree. So if I have 4 turning points, the minimum degree that I can have is 5. Now, I could have fewer turning points. I could have 2 turning points. I could have 2 or 4 or 0 turning points and still have a 5th degree. But anytime you have an x-intercept where the graph just touches, that's called a double root. And so that x-intercept would be a squared value. Example 3 asks us to graph the function and then identify the x-intercepts. So in example 3, I want to identify the x-intercepts first. How do I find x-intercepts? Some of you didn't know this for your last test. In order to find your x-intercepts, you set y equal to 0 and solve for x. So that means that I want to solve x cubed minus 4x equals 0. How am I going to solve this equation? What do I need to do? Do I have a common factor? I'm going to pull that common factor out, and then I'm left with x squared minus 4 equals 0. Does this factor? Does x squared minus 4 factor? It's the difference of 2 squares. So where will my x-intercepts be? At 0, -2, and 2. Now I'm going to get my calculator out, and we're going to sketch this graph. So I type in my function x cubed minus 4x, and then I'm just going to hit zoom 6 to get a standard window, and there's the graph. Part B asks us to approximate the coordinates of any turning points to the nearest hundredth. How many decimal places is the hundredths? So how do I find the coordinates of this turning point right here? What do I do? Second, calc, and then I want to find the maximum value first. So I need to move my cursor to the left of that maximum value, to the right of that maximum value, and then hit enter. And that gives me a maximum at -1.15, and the y value is 3.08. So this point right here was at -1.15, 3.08. And then I'm going to do the same thing and trace over to find my minimum value. But I noticed the symmetry with respect to the origin, so I already know that this point's going to be at 1.15, -3.08. Do y'all see the symmetry with respect to the origin here? This is an odd function, so all I've got to do is switch the signs on the x's and the y's. So So my turning points occur at negative 1.15, 3.08, and positive 1.15, negative 3.08. What will my local maximum be? What is my local maximum value? No, not negative 1, 3.08. The local max and the local min are the y values. Where they occur is the x values. So what's my local minimum? Negative 3.08. All right, example 4. What is the degree of this polynomial? What is the leading coefficient? So the degree is 4, the leading coefficient is negative. What do I know about the end behavior of the graph? What will it look like? The degree is even, so what does that tell me about my endpoints? Are they in the same direction or opposite direction? Same direction. The leading coefficient is negative. Will that direction be pointing up or down? So it's going to have this shape. And on a written test, I'm fine if you just draw the shape. But on my math lab, I believe that they're going to want you to say this. As x approaches negative infinity, y, or f of x, is approaching negative infinity. And as x approaches positive infinity, the y's are approaching positive infinity. These arrows here just tell you what these x's and y's are approaching. So here, as x goes to negative infinity, y is going to negative infinity. As x goes to positive infinity, y is going to, that should be negative infinity. So the y's are going in the same direction towards negative infinity as the x's approach both positive and negative infinity. On example 5, a different function. What is the degree and the leading coefficient? For part A, the degree is 3, and the sign of the leading coefficient, it's negative 2. So what will the end behavior be? Are my ends going to be pointing in the same direction or opposite direction? Same? Opposite? I hear both. Let's discuss why. We have an odd degree. Remember, the O's go together. We have an odd degree, so they're pointing in the opposite direction. So are they going to look like this, or are they going to look like this? Which one? These are both pointing in opposite direction. Do I choose this one or this one? The first one or the second one? I choose the first one. It's not this one because this is negative. The leading coefficient is negative, so you start at the top and work your way down as you move from left to right. How would you write that using the arrows and the approaching notation? So we would have as x approaches negative infinity, what is f of x doing? It goes to positive infinity. And as x approaches positive infinity, f of x is approaching what? Negative infinity. All right, on the last couple problems, we're going to be looking at piecewise functions. Do y'all remember piecewise functions? We've looked at these before. Remember, they're just a function where we divide our function into we take three different functions and we graph them over different regions. So I'll call this equation 1 just for points of reference, equation 2 and equation 3, and we're asked to find f of negative 3, negative 2, 1, and 2. So when I find f of negative 3, will I use equation 1, 2, or 3? I'll use equation 1 because negative 3 is in between negative 5 and negative 2. I use equation 1, so that means that I'm looking at f of negative 3 is going to be equal to negative 3 squared minus negative 3. Well, negative 3 squared is 9, minus a negative 3 is the same thing as plus 3, and 9 plus 3 is 12. Next, I'm asked to find f of negative 2. To find f of negative 2, which one of these three equations do I use? Okay, I can't use both. I can't have a choice. This is a negative 2. Is x equal to negative 2 here? No, x is equal to negative 2 here, so I'm going to use equation 2. So that means in this equation, I'm going to plug in a negative 2 in place of x. So f of negative 2 will be equal to the opposite of negative 2 cubed, because this function says take the opposite of whatever x is cubed. Negative 2 cubed is negative 8, so this becomes the opposite of negative 8. And the opposite of negative 8 is positive 8. Next, I'm asked to find f of 1. which one of these equations will I use to find f of 1? I'll use 2 because 1 is in between -2 and 2. So f of 1 is going to be equal to the opposite of 1 cubed, and that is -1. And then finally, I'm asked to find f of 2. Which equation do I use if I want to find f of 2? Number 3, not number 2, because x is not equal to 2 here, x is equal to 2 here. So I'm going to use equation 3, and that's going to give me f of 2 equals 4 minus 4 times 2, and that's going to be 4 minus 8, and that is -4. All right, on the last problem, we're asked to complete the following for this function. Part A asks us to sketch a graph. So for x's between -4 and 0, including -4 and 0, I'm graphing this quadratic function. So that means that if x is equal to -4, I get -4 squared is 16, half of 16 is 8, and 8 minus 2 is 6. So when x is equal to -4, y is equal to 6. I have this point at -4, 6 on the graph. When x is equal to 0, I end up with y equals -2. So I put a closed circle there. I need another point in between to check the curve. Because of the half, I have a feeling that I'll get a nice number here with -2. If x is equal to -2, that it gives me half of 4 is 2. 2 minus 2 is 0. I have another point here. So I'm connecting these points with a quadratic shape. And because I have endpoints here, definite endpoints, I have dots here that are filled in. On my next graph, between 0 and 2, I graph a linear function where the slope is equal to 2 and the y-intercept is 2. So between 0 and 2, I have an open circle here, but it's already filled in. Let me use this. So I have an open circle here for this second one. And then when x is equal to 2, I get a point right here. And there's the graph of this second function. And then when x is between 2 and 4, I'm graphing a constant function. So there's 2 to 4. I graph the constant function y equals 2. So I've done part A. I've sketched a graph of the function. Part B asked me to determine if this function is continuous on its domain. Continuous just means that I can go sketch it from one end to the other without lifting up my pencil. There's no point of discontinuity. Even though I have open circles here, it matches up at the endpoints where I did have closed circles. Do y'all see that? So for part B, this graph we would say is continuous. Part C asked me to solve the equation f of x equals 1. So if I just draw a horizontal line here at f of x equals 1, I see that I'm going to have 2 points where I'm going to have the equations the same. In order to find those points of intersection, all I've got to do is set the red function equal to 1 and then set the blue function equal to 1. So in order to do part C, I need to solve 1/2 x squared minus 2 equals 1, and the blue function was 2x minus 2 equals 1. I just set each of these functions equal to 1. That's this graph right here, and that will give me where these graphs intersect. So to solve this equation, I'm going to add 2 to both sides, and that gives me 1/2 x squared equals 3. Then if I multiply both sides by 2, I get x squared is equal to 6, which means x is equal to plus or minus the square root of 6. I'm only worried about the negative square root of 6 because the positive one's not in the domain of this piecewise function. So here I end up with x equals negative square root of 6. When I solve this equation, I end up adding 2 to both sides, and I get 2x equals 3. When I divide both sides by 2, I get x is equal to 3/2. So my two solutions here are going to be x equals negative square root of 6 and x equals 3/2. That means that this point right here is at negative square root of 6, 1, and this point right here is at 3/2, 1. All right, any questions? No? Then we're good, and this wraps up section 4.2.